Okay, so just go through the statement. What does the statement says? If I have any non-empty subset of non-negative integers, that is if A is not empty, subset of this set 0, 1, 2, 3 and so on, then there exists A in A such that x is less or equals to A is less or equals to x for all x in A. Okay, so this is your well ordering principle. Okay, that if I have any non-empty subset of non-negative integers, then A will definitely have a smallest element or a least element. I hope I am clear with the well ordering principle. Like for example, you consider any subset, non-empty subset, say 2, 3, 5, 9, 13. So this is a subset of this set and the least element being 2. Getting my point? So the well ordering principle says if you have any non-empty subset of non-negative integers, then it will have a least element. Getting my point? Any confusion?
No, sir.
Okay. So let me give you a proof of the division algorithm. Division algorithm is basically a very simple application of well ordering principle. So let me state the algorithm firstly. So what is the division algorithm? Given any integers A and B with B not equal to, consider B greater than 0, then there exist unique integers Q and R such that A can be written as BQ plus R greater or equals to 0 less than B. So this was the statement of the division algorithm, right? So we are just considering B should be positive and A can be any integer. Okay? Next, so you see what I'll do, how to prove this, that to see the proof has two parts. One is of existence, one is of uniqueness. So first I'll prove the existence of Q and R. I'll talk about the existence, how to find this Q and R. You consider this set. Consider the set S equals to A minus Bn such that n is an integer and A minus Bn is greater or equals to 0. Now I am considering this set. I'll tell you why I am considering this set. Now the set has the form A minus Bn where n is an integer. Okay, and this quantity is greater or equals to 0. That is, this is a set of non-negative integers. Do you agree with me? Now basically you see from here R will be of the form A minus BQ. Just to see, this is just for making you understand. You see from here R is of the form A minus BQ. Right? R is of the form A minus BQ, and see R is greater or equals to 0. That we know. That I have to prove. I have to prove these two things firstly, right? So that is the reason I am considering set of this form A minus B some integer n. Okay, here it is Q, but I am considering any integer n, and all, since R is greater or equals to 0, I am considering this as greater or equals to 0. I'll prove that this set contains R. We'll prove that. I hope you got my point why I am considering this set. Now firstly I'll prove that S is non-empty. This set contains some element. Okay, so claim S is non-empty. S is non-empty. How? You see, since B greater or equals to 1. Do you agree with me? B is greater or equals to 1 because B is greater than 0. So that means B is greater or equals to 1, right? What I'll do is I'll multiply both sides by modulus of A. Since modulus of A is a like positive number, the inequality will not change. So modulus A times B greater or equals to modulus A. Do you agree with me? Since modulus of A will definitely be a positive number, so I am multiplying both sides by modulus of A. Clear? Now you see one thing, I'll add A both sides. A plus modulus of A times B greater or equals to A plus modulus of A. I'm just adding A both sides. Okay? Now, what can you say about A plus modulus of A? Is it always positive? Do you agree with me? What will be A plus modulus of A for any integer A?
2A or 0.
That is, if very good, if A is positive, this is equals to 2A, right? Or when A is negative or 0, this will be 0. So in any case, this is definitely greater or equals to 0. Do you agree with me?
Yes, sir.
If you have a confusion, you can ask me. See, when A is non-negative, that means A plus, this will become A. So A plus A is 2A, which is definitely greater or equals to 0 because A was non-negative. And if A is negative, so this is minus A. So A minus A will be 0. So in any case, this is coming as greater or equals to 0. Now, what can this be rewritten? I am writing this as A minus B times minus modulus A. Just in place of this plus, I am writing minus of minus. So do you agree these two are same things? A minus B times minus modulus A. Getting my point? I am just rewriting this as this. Now you see what I am getting. That is what I am getting, A minus B times minus modulus of A, and this is greater or equals to 0. So what does this mean? You see this is a form A minus B times some integer n, right? This is the integer. So this is of the form A minus B times some integer, and this quantity, you see, this quantity is greater or equals to 0. So this quantity is greater or equals to 0. So what will this means? This means that A minus B times minus modulus of A belongs to S. Therefore, S is non-empty. Any confusion till here? Any confusion till here?
No, sir.
Okay. So what I am seeing, that is, thus S is a non-empty subset of non-negative integers. Do you agree with me? S is first of all non-empty, and why subset of non-negative integers? By the condition this. All the elements of S are greater or equals to 0. So this. So just now I stated the well-ordering principle that any non-empty subset of non-negative integers has a least element. Those who came late, just go through this one. So even S will have a least element, right? By this well-ordering principle. Okay. So therefore, by the well-ordering principle, S has a least element. Say, I am calling that element as R. I am calling that element as R. Clear? So I am calling the least element as R. That is, R belongs to S, and R is the smallest element of this set. Now understand my point very carefully. Since R belongs to this set, R will have this kind of form, because any element of S has this form. right? Any element of S has this form. So R will also have this form. So let me write it down. So therefore, there exists some integer Q such that R is of the form A minus B Q, right? Just instead of N, I am taking some integer Q, so R will have the form A minus B Q. And definitely R is greater or equal to 0 by the condition of the set S. Any confusion till here? Any confusion till here?
No, sir. No, sir.
Okay, so you see we have done half proof. How? See, from here what can I write? That is, A can be written as BQ plus R, and with the condition that R greater or equals to 0. With the condition that R greater or equals to 0. Getting my point? So what else I have to prove? I have to just prove that R is less than B, because I have proved this condition. I have proved that R is greater or equals to 0. Lastly I have to prove is R less than B. Lastly I have to prove is R less than B. So claim I am claiming is that R is less or equals to B. Sorry, R is less than B. That what I have to prove, R less than B. If I am able to prove this, we are done with the existence. So I have to prove this. We will take the contradiction. Suppose R is greater or equals to B, right? We have to prove that R is less than B, but I am assuming that suppose R is either greater or equals to B, then definitely R minus B is greater or equals to 0. Just taking B on the left, so R minus B is greater or equals to 0, right? Now in place of R, just to put this, what is the value of R? A minus BQ. So A minus BQ minus B greater or equals to 0, right? In place of R I am putting A minus BQ. So A minus BQ minus B greater or equals to 0. So A minus, just take B, just take minus B common, so minus Q plus 1 times B greater or equals to 0. Clear till here? Now you see,
Yes, sir.
this is again of the form A minus B times some integer. See, elements of S are the form, S is of the form A minus B times some integer, and this should be positive, right? Sorry, non-negative. And similarly, A minus B times some integer, and this is non-negative, so this means that this element will also belongs to S. Do you agree with me? This element will also belongs to S. But you see, what is this element? This element, just trace back, this is same as this is same as this, so this element is same as R minus B. You see, just trace back, this actually means this, and this actually means R minus B. So this is exactly equals to R minus B. Getting my point? And R minus B is definitely less than R. Why? Because B is positive, so R minus B is definitely less than R. So what have we got here? That this element belongs to S, and this element is less than R. Is it possible? Is it possible?
No.
Why? Why is this not possible?
Because R is the least element.
Very good. By my assumption, the least element of S was R. But if this belongs to S, then this contradicts that R is the least element of S. So, which contradicts the minimality of R. So that means this is not true, this is not true, this is not true, this is not true, this is not true. That means R cannot be greater or equals to B, so the only possibility is R should be less than B, and therefore what I got, A equals to BQ plus R with the condition that R is greater or equals to 0 less than B, and this proves the existence part. Existence is done. Any confusion about the existence? So I have proved that there exist integers Q and R which will satisfy this relation. So next I have to prove the uniqueness part. You see, there is something called as uniqueness. That means only one Q and only one R will satisfy this relation. Okay, so let me give you the proof of the uniqueness part. So uniqueness of Q and R. So what is the usual way of proving the uniqueness? What we do, we assume that suppose there are two values of Q satisfying the given relations and there are two values of R satisfying the given relations, then we show that those two values must be same. So that usual way we'll use, suppose A has two representations. That means A can be written as BQ plus R, where R is greater or equals to 0 less than B, and A can be written in the form BQ dashed plus R dashed with 0 less or equals to R dashed less than B. This is the usual way of proving the uniqueness. What I have to prove, that to prove Q equals to Q dashed and R equals to R dashed. Got my point till here? I have to prove these two things. I am assuming there are two representations of Q. Now, since both being the values of A, so this must be equal to this. This is also the value of A, this is also the value of A. So this must be equal to this. So let me write it down. So therefore, BQ plus R equals to BQ dashed plus R dashed. Send this term here. So if I take B common, Q minus Q dashed equals to R dashed minus R. Any confusion till here? Take mod both sides. So this will become modulus of B times Q minus Q dashed equals to modulus of R dashed minus R. And since B is positive, B is greater than 0, so B comes out of the modulus of Q minus Q dashed equals to R dashed minus R. Any confusion till here?
No, sir.
Okay, now we see. Now, what I know about R dashed. R dashed, let me write about R. So I know that R is greater or equals to 0 and less than B, and I also know that R dashed is less than B, greater or equals to 0, right? I need a negative sign, like I need the range of minus R, because see here it's minus R. So this implies if I take minus, if I multiply by minus, so the inequality gets changes, so this becomes greater than minus B, less or equals to 0. Am I clear till here? Why I am doing this? Because I need the range of minus R. So I know this is the range of minus R, I know this is the range of R dashed. Just add these two. So on adding, what will I get? R dashed minus R, B plus 0, this is B and this is greater than minus B. Right? Okay. Can I write from here? Modulus of R dash minus R is less than B. You know this result. Let me state here that mod x less than A actually means x greater than minus A less than A. I hope you know about this result, right?
Yes, sir.
Yeah. So consider this as x. So x is greater than minus B less than B. So that means modulus of x is less than B. Clear till here? So just like this is less than B. So using this in 1, we get, what will I get? B times modulus of Q minus Q dashed, and this is less than b, so I'll get eventually this is less than b. Since b being non-zero, I can cancel b from both sides to get modulus of q minus q dashed is strictly less than 1 since b is not 0. Right? So I can cancel b, and you see one thing, and definitely positive also, right? Or else the inequality will change. So since b is greater than 0. Now definitely modulus of any number is definitely greater or equals to 0. Okay, modulus of any number is greater or equals to 0. Modulus cannot be negative. Now you see, you are getting something like this. Modulus of x is less than 1, greater or equals to 0. What is the only value of x satisfying this, provided x is an integer? What is the only value of x satisfying this, provided x is an integer? Yes, x equals to 0 is the only possible thing, provided x is an integer. So I know that q minus q dash is an integer. So what should I write? The only thing is q minus q dash must be 0. And that implies q must be equals to q dash. So I've done the proof for uniqueness of q dash. Now again, using this in 1. So you see, in 1 I am putting q equals to q dash. What I am getting, I'm getting a 0, so b into 0 is 0, so what I am getting is modulus of r dash minus r is 0, and that implies the only possible thing is r dash equals to r, and hence the uniqueness and the existence both have been proved. If you have any confusion regarding the proof, you can ask me. Okay, I hope you are clear with the proof. Very good. So this was the proof of the division algorithm. Okay. Now, in the division algorithm, we had assumed like a can be any integer, but what we are assuming is b is greater than 0. But now we will prove this is true for any non-zero b. So a more general version. Okay. I'll prove the more general version of the division algorithm. More general version, okay? So what does the general version says? Given integers a and b with b not equals to 0. B can be negative or positive, but b cannot be 0. Then there exist unique integers q and r such that a can be written as bq plus r 0 less or equals to r less than modulus of b. Okay, here comes the extra part, modulus of b. Okay, so I'll do the proof. So once I'll consider b greater than 0. So when b is greater than 0, see, b not equals to 0 means b is either positive or negative. So when b is positive, we are done, because if b is positive, I just did the proof here. So this was the whole proof if b is positive, right? So done. So we just have to show that when b is negative, the result holds. Any confusion? B not equal to 0 means b is either greater than 0 or less than 0. But when I am considering b greater than 0, which is nothing but the division algorithm, right? Because instead of mod b, like for a positive number, mod b will be b, right? So I just have to show the proof when b is less than 0. Okay? Then modulus of b is greater or equals to modulus of b is greater than 0. Any confusion till here? If b is a negative number, if I am taking the modulus, that will definitely be a positive number. Modulus cannot be negative, and since b is non-zero, modulus cannot be 0. Now apply the division algorithm again by taking this as the divisor. Take a to be the dividend and this as a divisor. So by this is positive, this number is a positive number, so I can apply the division algorithm. So by the division algorithm, what I can write is there exists unique, say some integer q dashed and r, such that a can be written as modulus b times q dashed plus r, and r is satisfying greater or equal to 0 less than modulus of b. Any confusion till here? Any confusion till here? Okay, so I hope you understood why I can apply division algorithm, because modulus of b is a positive number. So by that way, so this implies a can be written as, what is modulus b? If b is negative, if b is negative, modulus b is minus b. And a can be written as b times minus q dashed, just manipulating things, or a can be written as b times, call this as new integer q, where q is equals to minus q dashed, and that completes the proof. You see, a can be written as bq plus r, and what I have to prove. So this completes the general version. Am I clear till here? Any confusion? Just go through it, very simple. So whether b is negative or positive, from here what we are getting, that the remainder cannot be negative. Remainder is always greater or equal to 0 less than the modulus of that number. That means whatever a and b you choose, the remainder cannot be negative. The remainder is always positive. So let me give you a few examples following from the division algorithm. Like consider a is 13.
So
Yeah. Can you tell me what will be the expression here?
minus 20 equals to minus 8
Yeah.
into 3 plus 4.
Yes, that is correct, and that is the only possible thing, because remainder should be less than 8, right? Any confusion to anyone? So we learned the division algorithm, even the more general version. So we are interested in the division algorithm when the remainder is 0. So when the remainder is 0, a can be written in the form bq, and from this motivates the definition of divisible, which I gave you yesterday. So an integer a is said to be divisible by an integer b not equal to 0 if the remainder is 0. That is, if a can be written as bq. And how do we represent this? By writing b divides a. So this motivates the definition of divisible. Okay, and yeah, if remainder is 0, so b can be now negative as well as positive. Okay, so by the way, this I should tell you, this q is called as quotient and this r is called as remainder. Okay, so I give you the divisible. Okay, done. So let me give you a small theorem based on divisible. For integers a comma b comma c, the following holds. Number a divides 0, a should not be 0 first of all, 1 divides a, and a divides a should not be 0. So this I already gave you the proof yesterday, right? The proof of this one I already did yesterday. It was very simple. Here I give you the proof, right? So this is the first thing. I am not going to prove this one, that is up to you. So proof is done. Number B, second one, A divides 1 if and only if A is plus or minus 1. So I will leave this up to you. It's very simple. If you cannot do, you can ask me. This will be your homework. If you cannot do, like once you assume that A divides 1, then you have to prove that A, the only possible values of A are plus minus 1. Or once you assume this, A equals to plus minus 1, and you have to prove that A divides 1. The converse is very simple. The other side you think of it. It's very easy. I'll do from number C. Number C is if A divides B and B divides C, then very obvious, A divides C. Okay, I'll do the proof for number C. So the proof being, suppose A divides, these two are given to you, you have to prove this. So since A divides B, there exists Q1, consider, over Z. This is just by the divisible definition of divisibility. B can be written as A times Q1. Do you agree with me? Just by the definition, A divides B means B can be written as A times some integer, right? And since B divides C, there exists Q2 over Z such that C can be written as BQ2. Any confusion? Now what I have to prove? I have to prove that A divides C. That means I have to prove that C can be written as A times some integer. So I will start from BC. So this implies C equals to, in place of B I'll put is AQ1. So in place of B I'm putting as AQ1 and this is Q2. So this implies C can be written as A times Q, where Q is Q1 times Q2 an integer. So this, therefore, from what does this means? That A will definitely divide C. Just look at the definition of divisible. Do you have any confusion while understanding this proof?
No, sir.
It's very simple. Just go through the definition of divisible. Just very straightforward. Okay, then let me go to the fourth property. D. These are very small results that you should remember, and you can just prove these things just using the definition. What does the fourth proof is? A divides B and B divides A if and only if A is equals to plus or minus B. So this is the fourth one. I'll be doing the proof here. So what I have to prove? It is given that, like, I have to first assume this and prove this, and next I have to assume this and prove this. So let me start with this part. Suppose A divides B and B divides A. I am assuming this. What I have to prove? That A equals to plus minus B. Now what should be the first thing? Just apply the definition of divisible. So B can be written as A times some integer and A can be written as B times some integer. So then there exists Q1 comma Q2 over Z such that B can be written as AQ1 and from here A can be written as BQ2. Any confusion till here? Just following the definition. B can be written as A times Q1 and A can be written as B times Q2. Okay, now look here. A equals to, what is the value of B? B is A times Q1 Q2, sorry, AQ1. So B is A Q1 Q2. Now if I am assuming this, A divides B and B divides A, I should write a line here. Then neither A or B can be 0. Right? Just by the definition of divisible, if A divides B, then A cannot be 0. And if B divides A, B cannot be 0. You see, it was given in the definition itself. A divisor cannot be 0. A divisor cannot be 0. Right? So since is given A divides B, so A cannot be 0, and since it is given B divides A, B cannot be 0. Now because A is non-zero, I can cancel A, so what I am getting is Q1 times Q2 equals to 1. Any confusion till here? Okay, are you getting my point or no?
Yes, sir. Yes, sir.
Okay, now tell me, remember Q1 and Q2 are integers, so tell me what integers will satisfy this relation Q1 Q2 equals to 1. So let me write it down again. So Q1 times Q2 equals to 1, and Q1 comma Q2 are both integers. So tell me which integers satisfies this.
1 and 1 and minus 1 minus 1.
Very good. The only integer satisfying this is either 1 1 or Q1 equals to minus 1, Q2 equals to minus 1. For all, like, other than this, there are no values satisfying this. Okay, so from here, what is the value of, wait a minute, is B, Q2. Okay, so I'm just interested in the values of Q2. I'll tell you why. So what are the possible values of Q2? Either 1 or minus 1. So plus, minus 1. So therefore A, you see what was A? What was A? A was BQ2. So A was BQ2, but Q is plus minus 1, so this will imply plus minus B. So that is, I have proved that A is plus minus B. Now the converse part. Any confusion while understanding the proof?
No, sir.
Okay. Suppose, converse part, suppose A is plus minus B. What I have to prove? I have to prove both of these things. A divides B and B divides A. Straightforward. So this means what? A can be written as B times either plus 1 or minus 1. Just by the definition of divisible, this means B divides A. Right? Because this means A is of the form B times either 1 or B times minus 1. And if A can be written as B times some integer, that means B divides A. And again, A equals to plus minus B. From here I can directly write B equals to plus minus A, that is B equals to A times plus minus 1, and again by definition of divisible, this means A divides B, and this completes the proof. Go through it, very simple, go through it. I hope you got the proof. Okay then, now this was property number D, right? Now two properties are very important. Property E is very important. We'll use this property. If A divides B and B is not 0, then modulus of A is lesser or equals to modulus of B. That means when B is not 0, then the divisor is always less than the dividend. Getting my point? So this is what the proof says, that the divisor cannot exceed this one, like the dividend. That is obvious, but we have to prove it. The proof is very simple again. Since B is not 0, let me write it not this one. Since A divides B, then just by definition, apply the definition, B there exists Q over Z such that B can be written as A times Q. Right? Now note one thing. Note that B not equals to 0 implies Q not equals to 0. Why? Because if Q is 0, then B will be A into 0, and hence B becomes 0, which is not true. B is not 0. So since B is not 0, the question cannot be 0. right? So this q should not be 0. Clear? So now take modulus, because I have to take the modulus to get the proof. So taking modulus, so modulus of b, and this will become modulus of a times modulus of q. Clear? Now very simple. Since, I should write here only, since q not equals to 0, that means modulus of q is greater than 1 or greater or equals to 1. Getting it? Q is not 0. So Q is either negative or positive. So the values of Q can be minus, plus, minus 1, plus, minus 2, plus, minus 3. In any case, modulus Q is greater or equals to 1. So just use this result here. That means modulus of B will be greater than equals to, just modulus of Q is greater or equals to 1. So this will be greater than equals to modulus A times 1. And that is the proof. That is modulus A less or equals to modulus B. And that completes the proof. Go through it. Any confusion while proving it? If you have anything to ask, you can ask. Okay, so I'll proceed further then. I hope am I clear with all these things? Just apply the definition and do it. There can be other ways of proving this, okay? You can just try by yourself also. Okay, now going to the last one of this theorem. Another very, very important one which I'll be requiring it later on while teaching you GCB. Now, if A divides B and A divides C, then A divides bx plus cy for any arbitrary integers x and y. So you see this, if A divides B, A divides C, then A divides all the linear combinations of B and C. And by linear combination here, I mean that x and y should be integers. We are only dealing with the integers here. So if I use the term a linear combination, you assume that x and y must be integers. So the theorem says that if A is a divisor of B as well as C, then A will divide any possible linear combination of B and C. So I'll just give you an idea what I mean to say is, before going the proof, I'll just show you an example. 3 divides 6 and 3 divides 12 or say 15, right? So 3 will divide 6 times any integer and 15 times any integer. You can put here any integer. 3 will definitely divide. If I put here 2, if I put here minus 3, you just check. Minus 45 plus 12 minus 33, 3 divides minus 33. You can put here any integers. So this is what the theorem says. If an integer divides two integers, then that will divide all the linear combinations of the two integers. Okay? I hope you understood the meaning of this theorem. So let me give you the proof now. Proof is very simple. Since A divides B, there exists Q1 over Z such that B can be written in the form A times Q1, and since A divides C, there exists Q2 over Z such that C can be written as A times Q2. Any confusion till here? Now, what I have to prove? I have to prove that A divides this. That means I have to prove that bx plus cy can be written as A times some integer. If I can prove this, then we are done, because just that will follow from the definition itself. So I will start from here. I'll start from bx plus cy. I will prove that bx plus cy can be written as A times something. So for any integers x comma y. So what can be written? What can I write? Bx plus cy. In place of b, just put aq1. In place of b, just put aq1. So sorry. In place of b, I am putting aq1 x, and in place of c, you put aq2 and there is a y. Just take a common, q1 x plus q2 y. And definitely this is an integer. Q1 is an integer, x is an integer, q2 is an integer, y is an integer, and integer is closed under addition and multiplication. So this means a times q, where q is q1 x plus q2 y belonging to integer. So what you are getting, bx plus cy can be written as a times some integer. So what does this means? A divides bx plus cy for any integers x and y. Any confusion here?
No, sir.
Got the proof? Is very simple. It's very simple. Just follow from the definition. Do you have class after this also?
No, sir.
Okay, I'll just take 5-10 minutes more. I hope nobody has a problem. Okay, just 5 to 7 minutes more. I hope you got this thing. Now we are done with the theorem. Now just we'll enter a new part. Just I'll give a beginning. Now just note the divisors of any integer occurs in pairs. Now this is obvious. Why? Since if A is a divisor, then so is minus A. Do you agree with me? If A is a divisor, then so is minus A is a divisor. So the divisors will always occur in pair. For example, the divisors of 9. You see the divisors of 9. Divisors of 9. So what are the positive divisors of 9? 1, 3 and 9. And what are the negative divisors? Minus 1, minus 3, minus 9. So the divisors will always occur in pairs. And I hope you are clear with this statement. If A is a divisor, then so is minus A. You can try to prove it in just one line. Okay, so the divisors always occur in pairs. Now second thing you see, so from now onwards we will no more be interested in the negative divisors. Why? Because once the positive divisors are known, I can definitely find out the negative divisors just by writing a minus here. So from now onwards we will only talk about the positive divisors of a number. We will not talk about the negative divisors, because once the positive divisors are known, we definitely know about the negative divisors. I hope I am clear. So we will only talk about the positive divisors. Okay. Now let me just give you a definition now. Something called as common divisor. An integer d not equals to 0 is called a common divisor of A and B integers if d divides A and d divides B. I hope the definition is very straightforward. We'll call a integer d a common divisor of integers a and b if d divides a and d divides b. Right? Like for example, 3 is a common divisor of both 3 and 9. Okay. Now, first thing, 1 is a common divisor for any two integers a and b. You know why? Why is always one is always a common divisor of a and b? The results follows from here. If you remember, just from here, 1 will divide a, 1 will divide b. Just by the definition, it is clear that 1 is a divisor of a and b. So you give me any two integers, I will definitely find a common divisor. That is 1. 1 will always be a common divisor. So the collection of all the common divisors of a and b is non-empty. Okay, so if I am collecting all the common divisors of say two particular integers a and b, okay, then definitely that collection will contain 1, so the collection is non-empty. Now my question, will this collection be finite or infinite? Collection of all common divisors for some particular a and b, will it always be finite or it can be infinite?
So we are considering two finite numbers a and b, right?
Right. Definitely. Numbers are always finite, like we are in integers. So, what do you think? What about this collection of common divisors? Finite, infinite, or in some case finite, in some case infinite? What can you tell me about it?
So I guess it should be finite, so.
Okay. Anyone else?
Finite.
Sorry? It will be finite in all the cases except one case. You see, if a and b are both 0, if a and b are both 0, then what do you understand from here? Okay, a divides any integer. So any integer, 1 divides 0, 2 divides 0, 3 divides 0. So then every integer, every non-zero integer is a common divisor of both a and b. Do you agree with me? If both the numbers are 0, then every number is a divisor of both the numbers. Both are 0. I am considering a as 0 and b as 0. So every integer is a common divisor of both a and b. So that collection will be infinite in this case. Agreed or no? Do you agree with me? Or do you have a confusion?
It's clear, so.
Yeah. Okay, but we are not interested in this case because every number is